Hello students. So we are here again and we will be taking our study forward in the moment of inertia. So first of all, what we learned yesterday, let's take a practical of it. Let's take a practical. So this is an object, this is a rigid body collection of particles, and this is a rod, of course. What am I going to do is just arrange this like this. What is this? What this becomes? Now I can rotate this. Easily. See, this is rotating easily. About what? About an axis. This can be anywhere on this. And rotate. Like this. So that's an axis. It's an axis, right? And which kind of an axis? So where it is rotating? It's rotating in a horizontal plane. It's rotating horizontally like this. It's a horizontal plane, correct? It's a horizontal plane. Horizontal. And where is axis? Oh, the axis is vertical. Plane perpendicular. This horizontal plane, and this is plane perpendicular axis. And also passing to the center of this, the center of mass of it. So it's a centroidal axis. What it is? It's a centroidal axis. And now see this. Now how it is moving. How it is rotating in a vertical plane. And where is the axis? The axis is horizontal. The axis is horizontal. It can be here also. The center can be here also. Anywhere on the axis. So there are so many particles. Like let's mark the particles. So say this can be a particle. It's moving around this. In this circle. Right? This particle. This can be this particle. It is moving around. In this circle. In the shorter circle. But in the same plane. When they move. So this particle. They move in the same plane. With a different radius about its axis. Which axis? Centroidal. Now, over here, still it can rotate. It can or not? It can. See, it can rotate. It can rotate about this. It can rotate about this. Depends upon. Okay, so, but this is not a centroidal axis anymore because it is not passing to the center. So, not a centroidal axis. But it's more easy. It has a higher moment of inertia. So, it's more easy in comparison to this. About this, we have the minimum moment of inertia. Less freedom. It's a little difficult. Over here, it's easy. It's easy because the freedom is more. It's more easy. Now, axis. Everywhere you can get an axis. See this? This whole structure can rotate about this axis. This will be the axis. So about this axis can rotate a whole structure. You can rotate the axis itself. And the whole structure will rotate along with it. Correct? Right? Okay. Just like the fan axis. That will rotate, so the whole structure will rotate. You know spinners and swingers. This is ball. You bowl it like this directly. Without using your fingers. Rotation on this. And then you rotate it like this. Come on. I have to fetch it. Let me fetch it. So, what if I do it like this? And what if I do it like this? That will be the difference between the spinning and the swinging. How the swinging and the spinning. One rotation is like this about a vertical axis. And second is like this about a horizontal axis. The difference between the spinners and the swingers. So, a whole lot of applications for the case of the axis of rotation. We did about the moment of inertia yesterday. We said that the moment of inertia depends upon some factors. The first of which was the mass. The second of which was the AOR, the axis. The third of this was the distribution of mass. And we said very concretely about the D, that is the shape factor, and which is K, the radius of gyration. the radius of gyration. We have a rigid body like this. We have this particle which moves in this circle. This particle. We have another particle which moves in this circle. I have another particle which moves in this circle. I have another particle which is moving in this circle. Right? These are the particles. These particles. What do? I locate the center of the circle, C1, the center of the circle, C2, the center of the circle, C3, the center of the circle, C4, and I connect them. So I connect them. This locus of the center of these circles, it defined as axis of rotation. So that's my AOR. These are all different points, but they all rotate with the same angular speed about this axis. So all the points C1, the point C2, the point C3, the point C4, all rotate with omega. All rotate with omega about this axis. That's the rigid body rotation. That's the rigid body rotation. Every particle may have a different mass and a different distance. This will be R1, this is M1, this is R2, this is M2, this is R3, this is M3, this is R4, this is M4. Different. And so the individual particle moment of inertia may be different. And then you can calculate the overall moment of inertia of the rigid body. Discrete system, where we said the net moment of inertia is supposed to be summation of mi, ri square, I ranging from 1 to n, where n is the number of the particles over there. So we did it for the two particles. We did it again. This has started Siri. Again, we did it for the 2 particles, 3 particles, 4 particles, 8 particles. No, we did not do for 8. So we do for, let's say, 8 particles right now. So we have the question with us. We have 8 objects, each of mass n, point mass objects, placed at the corners of the cube, and the rest these rods are massless, weightless. So we need to find a moment of inertia about an axis passing through one edge of the cube. Any one edge of the cube. Any one. So let's take this one. So about this axis. So let's mention this particular axis as y axis. So we need to calculate the moment of inertia about this particular axis, how much it is. Let's try this out. So we have 8 particles. So this particle moment of inertia is 0. This is 0. Do we know that? Yes. Why so? Because they lie on the axis itself. The perpendicular distance is 0. So we have 0 plus 0 for these 2 particles. In total we have 8. Now this particle, what is the distance from here to here? What is the side length? A. Okay. What about this particle? Perpendicular distance from here? Once again A. What about this particle? It's once again the perpendicular distance A. What about this particle? Once again the perpendicular distance is A. So there are 4 particles whose perpendicular distance from the axis is how much? A. So we have MA square into 4. So 6 particles gone. 7th and 8th. 7th and 8th are supposed to be these particles. This one. And so this is the distance. That's the perpendicular distance. What is the perpendicular distance over there? That is by hypotenuse. If this is A, this side is A. So this will become A root 2. This is for the 7th particle and this is for the 8th particle. The perpendicular distance once again this one. So once again this distance is how much? A root 2. So hence the moment of inertia for this will be plus m into root 2a whole square. Perpendicular distance and 2 particles. So multiplied by 2. That's your moment of inertia. So pretty simple. As we said, you can keep on doing it. You can keep on increasing the particles to 12 and so on and calculating. It will be easier. We got a crux of it, so it will be easier. So what's the overall moment of inertia? That's 4 and 2 into 2, 4. So 8 ma square. So we do have an option, C part, as 8 ma square is the moment of inertia. So we have revised whatever we did yesterday, right? So let's move forward and do a very nice question, very nice question. The question is like this. We have the particles, many particles, 100. So why to take 12, 14, 16, we decided to take 100 particles. Decided to take 100 particles. are kept at the marks 1, 2, 3, so on, and find the moment of inertia of the system about the perpendicular bisector of the meter scale. It's not telling center of mass. It's telling about the perpendicular bisector of the meter scale. Do we know what is a meter scale? We must. So that's a meter scale, and that's a 50 centimeter mark. So there are particles on both the sides, right? So let's sketch out the particles. So we have the particle here at the 49 centimeter mark. This is the 49 centimeter mark. This is 48 centimeter mark. This is 47 centimeter mark, and so on towards the left, right? So this distance will be how much? 1 centimeter. This will be 2 centimeter. This will be 3 centimeter, because the axis is passing through the 50 centimeter mark. So that's the axis. The axis is passing through this. Cool? Correct. And how much? 1 gram we have 1 centimeter, 2 gram at 2 centimeter. So over here that will be 49 gram. This particle. This particle is of 49 gram. What about this particle? This particle is of 48 gram. What about this particle? This is of 47 gram, and so on over here. So on over here. That means the first particle was somewhere here. That was at 1 centimeter mark. And this particle was of 1 gram. And the distance of it from here. Distance of it from here will be how much? 49. That will be 49 centimeter from here. Like this. This is the left side arrangement. Now the right side. Now the right side arrangement. So let's check on the right side arrangement now. So this is 51 centimeter mark. This one. This is 52 centimeter mark. This is 53 centimeter mark, and so on. So what about the distances? What about the distance? This is once again how much? 1 centimeter. This is 2 centimeter. This is 3 centimeter. And further, over here, we have 51 gram. Over here, 52 gram mass. Over here, so on. 53 gram mass. And the last one, over here, somewhere. That is a 100 centimeter mark. And the particle over here is of the 100 gram. And the distance of that particle from here should be 50 centimeter. That's 50 centimeter. And so there is a particle here at 99 centimeter, having the mass 99 gram, and the distance of that particle is 49 centimeter. That's the whole arrangement of this is. And now we wish to write the moment of inertia for this. So let's start writing. I will be writing this in two halves, two parts. Right? First of all, for the left side part. So beginning with this particle. Well, what is the mass? 49 gram. And distance is 1. So 49 into 1 square. Correct? mr square. This is 48 into 2 square. So plus 48 into 2 square. So on. And then 47 into 3 square. And so on. Until that will be this one. 1 into 49 square. Right? That's the moment of inertia for the left side particles. Then comes the right side particles. So for the right side particles, let's start. So that's 51 into 1 square plus 52 into 2 square. So on. Then this 99 into 1 square. And plus this last particle, that is 100 into 50 square. That's the moment of inertia of all the particles. M into r square, m into r square, m into r square, m into r square, so on. Now, if you check carefully, if you combine this, can you see this? You can combine this. Then you can combine this. Then you can combine this. If you combine these, the terms which I have written for you, what do we get? Check it. Combining these terms as this one, 49 and this one, that becomes 49 plus 50 into 1 square. Then the next one, that is 48 plus 52 into 2 square, and so on. So over here, you will get 1 and plus 99 over here. Right or no? That's adding up. 140, keep on adding it. That is 49 into 1 square and so on. And the last sum over there, that is 100 and into 50 square. That's it. Keeping adding. So what do we get? We get 49 plus 51. This is 51. This is 49 plus 51. So 49 plus 51 becomes 100. But that's 100 into 1 square. This one again 100. So 100 into 2 square. So on. And the last one, that becomes 100 into 50 square. That gets combined. And now the overall moment of inertia, that becomes 50 square. 100, sorry. Not 50 square. That is 100 common. And 100 common into the first term 1 square, the next term 2 square, and this goes on till 50 square. So that's what will happen if we take a large number of particles. It becomes that difficult. They have to form the series. If it is for 2 particles, 4 particles, 6 particles, directly done. Right? But if it becomes large, this problem arises. You will have to take the help of the sequence and series. Right? And if it forms a series, if it does not form a series, it will be task. So that is a sum of the square of the first and natural number, that is n into n plus 1 into 2n plus 1 upon 6, where n stands 50, and so that will be 100 into 50 and into 50 plus 1, 51, and into 2 into 50, 100 plus 1, 101 divided by 6. And into that's mr square. Mr square. Mass is in gram, R is in centimeter. So convert to kilogram 10 power minus 3 and centimeter to meter and square of it. Mr square. Converting to MKS, right? And then we calculate a value. So 326 and this is 17 and this is 25. So we get this calculation as 25 into 17 into 101 and into this. That is 10 power minus 7 and 100. So 10 power minus 5. So that's 25 into 17 into 1.01 into 10 power minus 3. And the units that become kilogram meter square. And on calculating this, you will get a value for the moment of inertia finally as 0.43 kilogram meter square after this much of an effort. And so with this now we will be signing off. We'll be signing off with the basic formula, that is for m1 r1 square plus m2 r2 square. We have elevated ourselves from single particle to 2 particle to 3 particle to 4 particle to 8 particles and to these 100 particles now, and that's enough. We had enough of it. We had enough of the discrete distribution, and now we should venture into the article of the continuous distribution, where we have the objects with us. The objects with us, the sphere, the ring, the cylinder, and the shapes which we are fascinated with, once again are going to come into our life. Recently we talked about this in the center of mass, and now once again in the moment of inertia. So continuous mass distribution is a collection of infinite mass particles, we know that, where a larger object can be broken into infinitely small elemental point masses. And we do remember, what do? We basically assume those tiny particles to be identical. So we assume a single particle dm, which is at a distance of r from here, from that axis. So this is supposed to be an axis, and this is our rigid body, and so this is one of the particle dm at this particular distance r square, and there are many more. Whose distances are going to vary out. Who's going to be vary out, and we are going to add up the little moment of inertia of every particle. Every small particle has a little moment of inertia. What is that? That is di. That is dm into r square, and the collection is so large that is not countable and it tends to very large. It's not 2, 4, 10, 20, 100. It is very large. So we have to take the help of what? Integration. So we integrate this particular function and calculate a value for the moment of inertia. That is the integral of dm into r square. The limits will come as per the structure. As per the way of integration, we will be checking in the limits such that all the particles are taken care of. Like we used to do in the center of mass. That is for the rod. You do remember 0 to L like that. Okay. So similarly. Or for the ring, half ring, we used to take 0 to pi. Something like that. Okay. We'll be once again doing that over here. But the basic formula is changed and it becomes integral dm into r square. That becomes. Okay. So moving ahead. Parallel axis theorem. What is this? We have two theorems with us. And what for these theorems are? See, we have already seen that the moment of inertia comes minimum about the center of mass axis, which is perpendicular to the plane. Right? About that axis, we get a minimum. Correct? And so we need to check about the different other axes also. So about the which axis? Oh, the centroidal axis. It is coming what? Minimum. Correct? And now we are going to check it about the different axes. So let's check it about the different axis. So different axis comes another axis, which is this axis. Let's label the axis as PQ. And this axis is the center of mass axis. That's ICM axis. And there is some distance between them. And that distance is supposed to be the perpendicular distance. Let's say that perpendicular distance is given as d. That's a perpendicular distance between these two axes. So we have two axes which are like this. And there has to be some distance between them. So there is some perpendicular distance between them. So this is supposed to be the perpendicular distance between them. And these are two parallel axes, right? So these are the two parallel axes. One of the axes is passing through where? The center of mass. The second axis passing from somewhere. Like I did in the practical over here also. Like I had two axes. So one axis was here. So this is supposed to be what? The center of mass axis. This is the center of mass axis. Right? And the second axis is supposed to be passing through here. Right? So this is the second axis and it is passing through here. Right? So these are the two axes. And these are two parallel axes. Okay? And then there is supposed to be the perpendicular distance over there. So that perpendicular distance, I will show you. Right? So you can see now. So that's the line which I have drawn. That's the perpendicular distance between them. That's labeled as what? D over there. So they have to be two parallel axes. This condition has to be there for checking up. For checking up, that has to be there. Okay. So now the theorem says that the moment of inertia about the PQ axis is equal to moment of inertia about the center of mass axis and plus m into d square, where m is the mass of the rigid body. This is defined as a parallel axis theorem. This theorem is a parallel axis theorem. Now you will be asking, where does it come from? So let me show you. So let's consider this as a rigid body and this as your center of mass. And so this is your center of mass axis. And I have another axis which is parallel to this. So let's label this as the PQ axis. And the distance between them as h. Like this. Or in this case it is d. So I can take this as d. Okay. Anything. D or h, whatever it is. Some books write h, some books write d. We are labeling d over it. Okay. Now consider a particle here. Let's say the ith particle. And drop the perpendicular. So that perpendicular is, let's say, r. The distance, the perpendicular distance. So, what's the moment of inertia about the center of mass axis? That will be summation of mi ri square. Simple. I from 1 to n. Mi ri square. Simple. Then, the same particle has a different distance from the PQ axis. The logic is too simple. The logic is that this particle is going to be rotating or moving in this circle about this axis, whose radius is Ri. While about this axis, it will have a larger radius, like this. And what is the value for the larger radius? This is Ri and plus d. So this distance over there, that's Ri and plus of d. The same particle distance. The particle does not move anywhere. We are selecting a different axis. We are selecting the different axis. We're taking a different axis. So if you are considering a particle here, so uska distance yahan se, the distance from there is this much, and then from this axis, from the second axis, from this axis, the distance is going to be different. What is that difference? Now this particle will have a larger distance from here, smaller distance from here, larger distance here. So obviously the moment of inertia about this will increase because this particle will be having a larger distance from here. Easy, it's easy. From here it is lesser distance, from here it is larger distance, so easy. That's what the theorem 4 look is, na? That this moment of inertia is greater than this. This is what it is saying. That IPQ is more than ICM. This is what it wants to say. Got the point? Yes, of course. So we are proving that. So what's the moment of inertia about a PQ? That is summation of Mi into Ri and plus d whole square. That's it. Now solve it. So this IPQ should be equal to summation of Mi into, open up this, a plus b whole square. So Ri square plus d square plus twice of Ri into d. Correct? Open up this. That becomes summation Mi Ri square first term, summation Mi d square second term, then summation twice of Mi Ri into d as the next term. Fine. Now see, what about the first term? If you look at the first term carefully, this one, this is same as this term, which is equal to ICM. This means instead of this you can write ICM plus d is a constant term. That's the constant difference between the two axes, fixed distance. So it comes out that's a d square summation Mi plus 2 is taken out, d is taken out, that's summation of Mi Ri. That is the value for IPQ. Does it match? Or still it does not match. So the next step, the moment of inertia about the PQ, that's equal to about the Cm plus what is summation Mi? What is summation Mi, my friends? That's the 0th moment of mass. Yesterday we did it. That's the 0th moment of mass. Can you see these terms? This is second moment of mass. This is 0th moment of mass. This is the first moment of mass. Summation r power 0 Mi. Summation r power 1 Mi. Summation r square Mi. Everything 0th moment, first moment, second moment in this equation. So summation Mi is a total mass, that is m into d square plus something plus twice of d. Summation of Mi Ri. My friends, very crucial point which I am going to speak, the golden words I am going to speak right now. The net moment of mass. Listen, the net moment of mass about the center of mass is 0. This is what we read in the center of mass article. Those who don't know, go and watch the videos in the center of mass article. What is the statement? What is the statement? The net moment of mass about center of mass is 0. And that's the reason that this theorem is necessary about COM. Because if this axis does not pass through COM, then this is not valid. It is not like that net moment is 0 about any axis. It is about center of mass axis. And therefore, summation of Mi Ri will become 0, but only about center of mass axis. That means what is the conditional behavior of the theorem? The condition of this theorem, the condition of the theorem is that one of the parallel axes must pass through the center of mass. must pass through center. There are certain things which are core essential for the rest study, and sometimes what happens due to like pandemic these days, what happens, a particular portion gets removed from the syllabus, a particular portion. So what? Rest of the syllabus is like that, and then in the future question that will come along, or you have to eradicate all such types of questions from everywhere, and that too from where? From CBSE or from competitive. Because 2022, when the students are going to write the paper, so will the same technicalities will be there, so we cannot take the chances. And that's the reason I am doing this theorem also in detail. Right? Okay, so it's an essential part. It's an essential part of rotation. If you don't know the axis behavior, then how do you understand the rotation? You cannot understand the rotation. The JEE syllabus, the NEET syllabus clearly mentions the axis has to be a fixed axis. But in the later stages, we also talk about an instantaneous axis. It's a rotation about a fixed axis. So you need to understand which axis and what is the behavior, which kind of axis it is. Is it centroidal or is it non-centroidal? Is it a parallel axis or perpendicular axis? You need to understand. So that's core part. Necessary condition. One of the axes must pass through C1. That basically reduces this term to 0 because summation MI/RI is 0 because of this condition, and hence you get the result that the moment of inertia about the PQ axis is ICM plus of M into D square. That's your parallel axis theorem. See, the center mass is not leaving us behind. It's there. It was yesterday also there. It is today also it is there. In the future also it will be there because it is one of the pillars of rotation. Moving ahead. That's the statement. Read it. It's very simple. The moment of inertia about an axis parallel to the center mass axis is equal to the sum of the moment of inertia about the center mass axis with the product of the mass of the system into the square of the perpendicular distance between the axes. That's so simple. That's so simple. If this distance is supposed to be d, so the moment of inertia about the given axis, that is a PQ axis, this one, is equal to about a CM axis, center mass axis, because this is supposed to be the center mass point preferably, and plus M into D square. That's your equation. Can we have two axes which can have the same moment of inertia? Let me frame a question for you. These are two axes. Okay. This is I1 and I2. So I1 is more than I2, or I1 is less than I2, or I1 is equal to I2. Which is correct? Which one is supposed to be correct? So we say anything can happen. Anything can happen. It depends upon where is the centroidal axis. As for this figure, locally, if we assume the center mass lies here, exactly here, so there will be an axis over here, like this, right? And this distance may be, let's say d1, and let's say this will be d2, and this is supposed to be IC. So how do we write I1? So I1 will be equal to ICM and plus M into d1 square. How do we write I2? That is supposed to be ICM plus M into d2 square. So what is the condition? Suppose d1 is more than d2. So therefore I1 becomes more than I2. If suppose the d1 is less than d2, so the I1 becomes less than I2, and if the d1 is equal to d2, then the I1 can be equal to I2. So what is the condition? You were not able to check the practicality, correctness, if you did not check in ICM. Directly they cannot be compared with each other. They have to be compared via the center of mass. Simple. It's simple. It's simple. Very simple. So, can we have more than one axis which have the same moment of inertia? Yes, we have these two axes. They can be infinite such axes. They can be infinite such axes means Means our favorite figure. Means our favorite figure like this. Now see this. See this. This is the center mass axis. So I can have axis here. The distance is this much. I can have an axis here. The distance is this much. I can have an axis here. Distance is this much. I can have an axis here. Distance is this much. So all these axes will be parallel and equidistant from here, and all these axes will have the same moment of inertia, and their locus can be a circle. The locus can be a circle like this, which have the same moment of inertia. So they can be infinite axes which can have the same moment of inertia. So cool things, so good things are coming across our way. That was our parallel axis theorem, and then we have the second bonus theorem, that is known as a perpendicular axis theorem, and also known as a laminar theorem. A laminar means a plane. It means a plane. So it's also known as a planar theorem. It's a planar theorem. So it is applicable only for planar bodies. We also have a 3D theorem for this. We don't get the questions from the 3D part of it. It's a 2D which is in our syllabus. That's a laminar theorem for the perpendicular axis theorem. And how do we state it? First of all, we have to select two axes which are in the same plane, and intersecting each other at this point. This is a point, and these are the two axes. One is the x-axis, second is the y-axis, and they are in the same plane. This is the same plane, right? This is in the same plane, in the xy plane, correct? Over here, and they are mutually perpendicular to each other. And from the same point where they are intersecting, I have a third axis. What I have? I have a third axis which is perpendicular to the plane. I have a third axis perpendicular to the plane. That's the z-axis. So the theorem says that the moment of inertia about this axis, which is perpendicular to the plane, that is Iz, is equal to the sum of the moment of inertia about the two axes which were mutually perpendicular and intersecting and in the same plane. Correct? Are you getting the point? Right? These are the two axes which are in the same plane and intersecting. So we can have two axes like this, and they need to be perpendicular. It's not necessary, it can be like this also. Still they are mutually perpendicular. So that's Ix moment of inertia, that's Iy moment of inertia along this axis, about that axis to be exactly. And then this will be Iz. That will be Iz. And this Iz is equal to Ix plus Iy. That's very simple to check. There will be a particle here. This will be having some distance from here. So it will be mi x1 square from here. And this, if you say as y, so it will be mi yi square. This is mi xi square from here and mi yi square from here. If you add it, it will be mi, because this will be the distance x and this will be the distance y. Okay, two axes are there. Okay, from one the distance x and second is y. So mi xi square plus mi yi square add up. So mi common, xi square plus yi square, and that xi square plus yi square will be this side, this one, because this is xi, this is yi, and this will be zi. This will be zi, the hypotenuse, and so that will be the perpendicular distance here. So that will be mi zi square, and that will be the moment of inertia here. It is that simple. Ix plus Iy equal to Iz. Two axes mutually perpendicular in the same plane, mutually perpendicular, intersecting at this point. Third axis through the same point, same intersecting point, and perpendicular to the plane, has a higher moment of inertia and is equal to the addition of the moment of inertia of both the axes. Like yesterday we did a question in which there were four particles, two small m and two capital M, and we checked the moment of inertia about a x-axis, about a y-axis, about which axis that came out to be maximum, about the z-axis. That was perpendicular to that particular plane. That's the maximum. Minimum we have checked out, minimum we have checked out. That's coming more in comparison to the two axes in the plane. How do we prove it? It's very simple. As I explained, consider a single particle here, having a mass of, let's say, mi over here, mi mass over here, this particle having a mass of mi, correct? And this distance from here, this one, let's say that is z. This one is z. Correct. The perpendicular distance of this particle from the x-axis, that is y, because this is having a coordinate x comma y. Why x comma y? Reason, because it's lying in the xy plane. It's lying in an xy plane. So any particle in this plane will have coordinate as xi, yi. And the perpendicular distance of this particle from the y-axis, this is the y-axis. So this distance will be how much? Perpendicular distance from the y-axis. So will be equal to how much? This one, this is on x. So this is xi. And the perpendicular distance from the x-axis, this much. Well, that's supposed to be yi. Correct? So the moment of inertia about the x-axis, that should be equal to mi xi squared summation. Correct? No. That's mi yi squared. Even if you make a mistake, the answer will be correct, but we should not make a mistake. So with x-axis, the perpendicular distance is yi. We're confirming from the two figures. This distance is supposed to be how much? Yi. From the x-axis. This is x-axis. So this is y. This is y-axis in this diagram. So that is x. Right? Anyone can be taken as an x and y axis. In this I have taken this as x-axis, this is y-axis. So anyone can be taken as an x and y axis, right? And then accordingly we can have the z here also. Here, this complete axis like this. Right? Now, the summation mi yi square about the y, that is summation mi xi square. That's simple. Y-axis perpendicular distance x, x-axis perpendicular distance y. Added, that becomes ix plus iy. That becomes summation mi into xi square plus yi square. Xi square plus yi square. If it is xi square plus yi square, use this triangle. Use this triangle. If you see it from the top view, it's more simple. You will be seeing it only the plane, only this plane. Where this is a particle. This is the x-axis. This is the y-axis. This distance becomes how much? Yi. This distance becomes how much? Xi. That's the perpendicular distance. And what about this distance? From here, we have that z-axis perpendicular to the plane. And from the top view, it looks like this. And exactly it is the z-axis. So that's the distance z. That's the distance z from the z-axis, this one. So this side is xi. This is yi. Pythagoras. I get xi square plus yi square as zi square from the diagram. So simple. So simple. So this becomes as summation mi zi square. That's ix plus iy. And what is summation mi zi square? That's iz. So we receive ix plus iy as equal to iz. As equal to iz. Right? So that's the moment of inertia theorem. That's the second theorem in line. And that's the theorem for perpendicular axis. So all the three axes, if you see, are perpendicular to each other. In the parallel axis theorem, the two axes were there, they were mutually perpendicular. No, parallel. In this case, all the three are mutually perpendicular. In the parallel axis theorem, we had a condition that one of the axes should be passing through center of mass. Such a condition does not exist here. This point which we have taken is not necessarily the center of mass. This point in this diagram is definitely the center of mass in this diagram. But over here, when I am selecting the point, it is not necessarily the center of mass. If the point passes through the center of mass, it's well and good. Even if it does not pass, still you can apply the theorem. But in the case of the parallel axis theorem, one of the axes has to be from the center of mass. In this, the condition is all the three axes have to be mutually perpendicular and passing through the same point. And two of the axes are lying in the same plane. That's it. And then we can happily apply this particular theorem. So there must be the statement of this, and that's a very easy statement. You can just put forward in the verse the same statement, that is iz as equal to ix plus I. That's the exact thing which it has written. It's a laminar theorem, explained that. It's a planar lamina. And the moment of inertia, the perpendicular axis theorem states moment of inertia of a planar lamina about an axis perpendicular to the plane. That's the z-axis. is equal to the sum of the moment of inertia of the lamina about the two axes at right angles to each other. So these are two axes which are perpendicular to each other in its own plane, intersecting each other at the point where the perpendicular axis passes, which means all the three are passing through the same point. In simple words, this is a long definition, but you put forward in very simple word. All the three are mutually perpendicular, two of them lie in the same plane, and all the three are intersecting, and all the three are mutually perpendicular. So the axis which is perpendicular to the other two axes lying in the plane will have a higher moment of inertia, and that is Iz equal to Ix plus Iy. Simple. So let's take the journey forward and let's try to calculate one derivation for today, and we will continue the good works tomorrow. So we have this for a thin rod, for a slender rod, a thin rod, and the axis is passing through the center of mass right now. This is the center of mass, and the axis is passing through the center. So that is supposed to be your ICM axis or the centroidal axis. I am writing IC. About this we need to calculate. The overall length of this is supposed to be N. That's a complete length of it. And the mass of this is supposed to be N. A 3D view can be like this. So this complete length is supposed to be N. The mass of this is supposed to be M. And that's your centroidal axis. We need to calculate the moment of inertia about this particular axis. How do we do so? So how do we do so? We consider a particle here, which is at a distance of x from here, and having a length of dx and having a mass of dm, and checking the perpendicular distance. So that perpendicular distance becomes how much? X. That becomes the perpendicular distance of the dm particle. So what's the moment of inertia of this particle? Di will be equal to dm and into x square. And if we integrate this, see, there are so many particles. There are particles here. There are particles here. So it's not a discrete distribution anymore. There are particles here. Everyone is having a different distance. So we need to represent one particle. That's our elementary particle dm. And the distance of this is x. And then we integrate this from this end to this end. This end to this end. But then we will be having this intuition, first of all, limit should be 0 to L. 0 to L. But that's not the case. That's not the case. If this is a rod and is supposed to be rotating about a vertical axis here, over here. So half of the particles are here and half of the particles are here. Half are here and half are here. So this is origin from where the axis is there. But the limit is not 0 to L. 0 to L will be if I consider an axis from here. Then all the particles are to the right of it. So that is from 0 to L. But now the axis is from here. So half is here, half is there. So limit should be minus L by 2 to plus L by 2. That explains, the limit itself explains that the axis is from the center. Correct. If you are holding it here, let's say L by 4, then the limit should be from here. It's minus L by 4, from here, minus L by 4 to plus 3L by 4. To plus 3L by 4. Getting the point? If you are holding here, then that's minus 3L by 4 to plus L by 4. And if you are holding from here, it is from 0 to L. That's how the limits are here. So right now we are interested in the center. But the limit is from where? Minus L by 2 to plus L by 2. That's it. And then you integrate this and you get your answer. It's a uniform rod. What it is? It is a uniform rod. So it's a uniform rod. I can use lambda as a dm upon dx as equal to m upon L since it is uniform. So I can write dm. So dm is how much? M upon L into dx and into x square. That's the value for di. And what do? I integrate this. So I'll get the moment of inertia as m upon L. X square dx becomes x cube upon 3. Limits pre-decided. Minus L upon 2 to plus L upon 2. That's m upon 3L into, place the limit, L cube upon 8 minus of minus L cube upon 8. X cube. So L by 2 cube minus L by 2 cube. This gets added. Don't subtract. It gets added That becomes twice of L cube by 8. This cancels as 4. That becomes m upon 3 and 4, 12. One of the L gets cancelled. We get L square. That's your moment of inertia. That's your moment of inertia. It cannot be just guessed. It has to be evaluated. In the case of the center mass, it was easily guessable that the center mass is going to be at the center from this idea. In this idea, center. But what is the moment of inertia cannot be guessed. Have to be calculated. So we have learned today that particular method, how we can calculate that. And about this axis, it is coming as ml square by 12, and this goes into your flashcards. It goes straight away into your flashcards, and you should be getting that particular result. Okay, with this I'm going to sign off today, and tomorrow we are going to meet and we'll be doing a lot of continuous figures. First of all, we will do the changes, variations in this. End axis, inclined axis, body axis, frames, and then we will be moving towards the ring center axis, tangent axis, and then the rim axis, then moving on to disc, then multiple rings, multiple discs. So much fun is going to come into tomorrow's lecture. So keep it watching. Right now I'm signing off. Bye.